All right, getting into actual mathematical modeling this time around. So DTM interpolation, this is what we're going to call global interpolation as we kind of walk our way through it. And I actually really enjoy doing this global interpolation stuff because it really helps easily visualize what's going on the ground. Because if you think like, okay, I'm going to show what the ground in Calgary looks like, and I'm going to have to create a model that a computer can produce. Well, if you go by like every single point, it becomes incredibly complex. But if I wanted to show Calgary, for example, and depending on the accuracy I need, I could easily put in like an exponential curve, for example, because it increases in elevation on one side and decreases on the other side as it goes north and south. So it's like it's a very, very powerful tool because once you have created your model, you can calculate a point on that model anywhere within the surface, and you'll know to what kind of predicted accuracy that you are getting it to be. So that is it's really the power behind doing global modeling. So we're going to apply interpolation functions to create mathematical terrain surfaces. And we're going back to this DTM process that we talked about in the first lecture, or last week. We are looking at the this reconstruction component, right? So we're going to create this DTM. We have the raw data. It's already been sampled. We've already got it from our data source. It comes to the surface. So this is what we're going to be creating mathematically. We're not creating a definite product at this point because I'm not creating a 3D visual or even a 2D visual. What I'm doing is creating the mathematics behind it. So this is like the reconstruction to the DTM surface, and then the validation comes in with the statistics that we're going to be examining. So just again, as a quick review of what we covered in last week, we have our representation of a terrain. We have mathematical and graphic types of representation. Then we have global and local, which in the mathematical side. And this time around, we are going to be looking at polynomials. In the next lecture, we're going to be looking at local mathematical models. And then the graphic stuff all comes later. That comes with the software that we're going to be dealing with when we're dealing with LiDAR, which is ArcGIS. So it's not even like it's a big secret. So that's what we're going to be working with, though. So these representations is what we're specifically looking at the math. We're not getting into Fourier and we're not getting into the other expansions, but we're going to look at polynomials. That means that we're going to be bringing in least squares, which is like the best part about 3D modeling, is looking at the least squares component. It was actually, to be honest, I never really understood the least squares until I did this. And the reason was that I could actually see it in like a visual format. It wasn't just numbers coming up. Like it was like, oh, this doesn't make any sense. This is where we're actually creating a final product, and that's what's really exciting about it. So some of the problems that we encountered before we get too hung up on least squares and getting all excited about that is that we really can't capture the full complexity of what is going on. So no matter what we try, no matter how many points we try to get, we're never going to capture everything. And that's where, if you do a LiDAR scan of all of Calgary, it's going to be huge. The data set's going to be enormous. And computers can't handle that. So we absolutely cannot get that full complexity. We can downsample it or undersample it, and then that will be the most effective way and most economic way. And then we will create our models from that. We also have an issue of the sampling accuracy. You go out and collect points. Sure, total stations are fantastic. They're so they're fantastic, but they don't cover a very large area. And as you start using a total station to do larger and larger and larger areas, the amount of samples you have is greatly reduced, and the amount of time and effectiveness. So the accuracy might be there, but then you think of the error of closure. That the further you go, the larger that ratio becomes, right? So the sampling accuracy is an issue. In LiDAR, we're going to spend a lot of time talking about accuracy with sampling and like what does LiDAR accuracy actually entail. And then we also have to worry about representation accuracy as well for the third problem. So let's say with LiDAR we have like all these different things that can impact the accuracy. And then we need to actually show the ground. So do I show it as a tin? Do I like create a model? And then do I take that model and create a tin from the model? Do I show that there is errors? Do I have the error bars that are built into it? Do I show the residuals? Do I give that as like a separate component, like I map that out? So this representation needs to be accurate. And sometimes you can have some really crazy model and it might be like, yes, mathematically my error is super close to 0, but it doesn't look anything like what the ground actually looks like. So again, going back to remote sensing, right? We have two really important things that we need to look at for accuracy. We need to look at numbers and we need to look at visual. So representation is a lot about the visual. Sampling accuracy ties in with the mathematical accuracy as well. So what do we end up doing? So we have all of these problems, and why do we have these problems? Well, we take our Earth's surface, which is a continuous surface. Then we create a discrete surface because we either do rasters or points, data points, like that's how we collect it. It's either in pixels or in data points. So that becomes discrete, right? Like, so every pixel is actually like its own little discrete unit. And then we got to convert it back to a continuous surface to be able to show the model. So we have data loss and data manipulation that's happening every single one of these steps. And so this is one of our biggest challenges that we deal with DTMs, because we have two conversions that are happening to take our Earth to a model that we can see on the computer or on a paper map. So let's look at the representation. So there are two general ways to represent a surface. We have our mathematics and we have our image, right? as always, every remote sensing thing that is out there, because this is all basically remote sensing. Even if you use a total station, by the time you get it into the model, it's become remote sensing. So we have our function, we have like this major function for the Earth's surface, we have the minor functions that we're taking ratios with, we're trying to figure out x and y's. It gets really complicated. Like, I mean, we're not going to get into like all the math here, but this is just giving you an introduction as to how 3D representations start coming together, because there's so much math that goes into this so that the computers can understand it. And then how do you even represent accuracies with that on top of it? So we have this continuous surface. We have a numerical representation of the terrain, right? Because we go out and we get this math model and we start working with this math model. We say, okay, now we can get some numbers. And really that's what we've done, right? Like you go out and you collect coordinates. Well, that's a numerical representation of the location that you are at. And really, absolutely, like everything's a circle. So, I mean, everything's like kind of an estimated location, because where is 0? As much as we like to say, yes, it's accurate to this point, it's accurate relative to something else. It's always relative to the coordinate system. So your coordinate system is also going to have an impact on this numerical representation. But what is really key is this whole issue of 3D space. So you have a single point, and that single point has 2 z values because it's got a straight cliff, for example. What happens? Especially if we put it into a pixel, right? Our computers handle pixels in a certain way. Which pixel do I show? Do I show the top one or do I show the bottom one? And because of this, and this is just, even with like, you put on goggles and you go through something and you're like, yeah, you know, I've got my virtual reality happening. What's going on around you is that the computer needs to calculate on straight edges, which of these z values am I showing? And so this is actually a problem, right? Because the pixel can only show one height, or the point can only be showing in one location. So how do I represent 3 dimensions? That's true 3 dimensions. DTMs are not true 3 dimensions. They are 2.5 dimensional representations. So if you are asked, does DTM there we go, does a DTM represent 3 dimensions? No, it doesn't. It represents 2.5 dimensions. And why? Because we can only store a single z value for an x and y location. We can't show 2 different ones. Okay. And if you were to say, well, why don't you just take the average of the 2? Well, now you've created a new model for that local that one single point, right? So it's not actually representing the true Earth surface. So all continuous surfaces are generally a local model, because they do have strange things that are happening like this. But like the Earth's surface is all continuous anyways, but we will still use global models, and we will look at it locally if we need to. So our surface is represented as smooth or discrete, right? Not smooth or smooth. So we can have flat edges like this. This is a tin, right? We've got our triangles, and the surface normal changes rapidly. It hits that edge and then the plane completely changes. So then my surface normals, which a surface normal is the direction of the slope. So it's so here, this is a good example down here. So we have our tangent to the surface. So these arrows kind of look like they're following the tangent. The surface normal is 90 degrees to that surface, to that surface tangent. So the surface normal is all going one direction on this plane, and then it all goes one direction on this plane, and it changes very, very rapidly along this line. That's considered not smooth. A smooth surface has a slowly changing surface normal. So it's, between the 2 triangles that was represented here, they slowly change from one to another. So you're going to see this like splay of arrows that move over this edge. So we need to show a smooth surface when we are using global models. So tins, they are not smooth. When we are using global models, which is representing the whole surface, the surface is now represented as smooth. So that nice smooth change between the 2 of them. So we have 2 major objectives that we're trying to achieve when we're trying to do this global model. The first one is that we're taking reality and representing it digitally. So we take a continuous surface and we create a discrete representation, and we do that through sampling, right? Because you can't pick up the infinitely small points all the way through the Earth's surface. So we have to sample it. Then our second objective is to take that digital representation or that discrete representation, and we model the reality. So this is done through interpolation. So the data collection is here. The digital representation, and this is the map creation, is here. So there are 2 ways of looking at doing modeling. There is interpolation and there's extrapolation. So interpolation is the process of estimating the values of an attribute at internal unsampled sites using measurements made at reference points. So keywords is estimating and internal. Okay, so the interpolation occurs within the range defined by the reference points. So just kind of reading the slides there for you. So estimation of points within a particular range that have not been measured, right? That's an interpolation. Extrapolation is kind of the mathematically more complex component of it, and that is predicting values outside of that data set. So it's the external unknown points. So a lot of, for example, climate change models, and I know this doesn't totally sit here, we're not really interpolating, right? Because a climate change model is predicting the future, saying, okay, if we have all of these different elements in this particular way, that means in the future it's going to look like this. Extrapolation works fine in Regina area where it's super flat. Like, okay, well, I've got these data sets here. I guarantee it's going to be within, a meter in this area right next to it, right? So that's not so bad. But if you go to the Rocky Mountains, good luck extrapolating, because really mathematically it is so difficult to extrapolate within a mountainous region. And that's why even avalanche modeling through microwaves and using all kinds of different slope models and such, it requires some extrapolation. And so the prediction models were always very poor. They're getting much better now. That the Swiss are really hardcore into avalanches. So they've spent a lot of time looking at microwaves and avalanche prediction. But extrapolation is all about that, what is going to happen in the future. It's that crystal ball, like what is it going to look like? Where interpolation looks at what's happening within the time frame or within that data set that we already know. So a good example would be with snow. An interpolation might be I do a snow pit. I'm looking at depth, looking at salt content because I'm on sea ice. So for me, really the height doesn't change that much, but snow depth does. Maybe I'm looking at the salt content at different layers, and then I can do one in one spot, one in the other spot, like maybe 15 meters away, and then I can try to interpolate between the two, saying the salt content and the depth of it are going to be in this way with my samples, right? So, and it's going to look like this, and it's going to impact my data sets in this way. So that's interpolation. So it's a little bit easier because now I'm within my data set. So extrapolation is a little bit more complex. so here is an example. So we have my reference points. These are the green ones that we go. Those are the ones that we've actually observed. If I'm interpolating, I'm looking at this red one. This is not something I have actually measured. It's something that I'm trying to figure out what, along this modeled line, what would my height be? Then extrapolation is like, what's happening out here? What do I think could be happening? What kind of other data do I have, right? So extrapolation is really predicting what craziness is happening outside of your data set. Earth surface extrapolation often takes into account like other data sets, so you end up kind of half getting data anyways, so it's not totally extrapolation. So another thing that I'm going to point out as we move into more and more of the math, so we're getting there. Notice that a Z with nothing on top, this is a Z value is going to be what you're measured. If you see the little hat on it, that is my calculated value or my modeled value. So it is, the hat means modeled. So we're looking at the modeled line. Measured is without anything on it. So anything mathematical has a little accent on it, little hat. So we're going to focus on interpolation, not extrapolation, because extrapolation is a heck of a lot more complicated. So the interpolation methods that we have is global and local. So for example, a global model looks like this. We come up with some sort of feature. I mean, this is a very complex model, but I look at the entire data set all at once and I interpolate. And so I can go here, for example, where there's no point, and I can say, okay, this is what the height of that point is, which is really helpful when you're trying to like design a highway or maybe build a bridge, right? Because you need to know what's in between. So interpolation is good that way. Then there's also the local interpolation, which is my local models. So I have this unknown point. I have all these points around it, and I'm just going to look at those points around it in order to calculate this point. So there's different ways to classify the interpolation. So there's global fit, which is what we're going to be looking at. It covers the entire area. It's one single function. So therefore it's quick, easy calculation after you've got it. Then there's local fit, which means you gotta, every time you try to interpolate, you have to search out points around it and then do the math every single time. Then we have something called an exact interpolator, which estimates the elevations at the reference points. We have an inexact interpolator, which means that I need statistics to find that data. There's a deterministic, which means that it has a value, so we can figure out what the difference between the interpolated and the reference points are. And we also have stochastic, which is using a statistical surface, which we'll talk about when we're looking at kriging. So we're going to look at global interpolation. We're going to look at trend surface analysis. So this is looking at creating a polynomial that identifies the surface itself. So one single function. So we have our original surface, and we represent, where we theorize that the surface itself is contained of two things. It has a trend and it has residuals. So this is two components that we're trying to figure out. What is the trend and what are the residuals for each point? The trend is defined by a model. It's the elevation defined by the model. The residuals is the elevation that is not defined by the model. So that's you can kind of think of it as the error of it. So we expect that the residuals will be 0 statistically, and we expect that the original surface is going to be the trend. So we want to minimize these residuals as much as we possibly can. And so but the key thing, and really important to note, is that the original surface and the estimated trend, okay, should have the same average. So if we're to add up all these residuals, they should equal 0. And then that means that the mean should be the same for both the original surface and the trend. So math. Yay, math. Here's our interpolation. So we have our model. We have a function that contains, so we have our observed known points. That's the elevation. We have a function that takes into account x and y, so that's the location where they're at in the horizontal, and all of my coefficients of my trend, then plus an error. So here is, this is I, which is my counter, which means that there's an n, which is the number of observations, so it's just counting from 1 to n. So I have my error. My error consists of my weight matrix and my standard deviation. Now again, my variance, that's standard deviation. Again, this is something that we will look at a little bit later. We're not worried about the weight matrix as much as what it's got here, but you'll see how it's kind of implemented. It's usually an identity matrix that we assume, and that's where it says it's approximately, right? So this would be an identity matrix, which means that we're just left with our residuals. So if we're to set up the least squares equation, L is my Z value. Okay? A is my design matrix, and X is my coefficients, and then plus E, which is my residuals. So here, again, showing this weight matrix is the identity matrix, and so we're kind of going to leave this out for most of the mathematics. We'll calculate that later. Now this might be an R, it might be a B, I don't know, maybe this is a B. I can't remember what SAM-A teaches, but these are the terms that I use in 3D modeling and how I learned them. So if you're seeing like a little bit of difference in variables, that's all it is just how we've learned them differently. So L is my observed Z values, okay? So we have M, which is the number of coefficients, and N, which is the number of reference points. You can see how the mathematics come together there. So polynomial equations, if you were to have to figure this out by hand, this is how you would do it. You'd have your sums, you'd have I and J, so this is my observed X and observed Y values, and they count differently all the way through. And we have coefficients that are associated with each order, right? So the order of X might be different than the order of Y. So we have normal equations. These should look familiar. So we're trying to isolate for X hat. So once we isolate for X hat, we have our N negative 1 and U. So if you go by that, if you like the N negative 1 and U, then you can definitely use that terminology for yourself. I'm not here to like examine whether or not you are using the exact same variable as I am, or that you only do it in the way that that I do, like whatever, if you have your own way of doing it that you found easier to understand with what Sam A taught, then stay with that, please, because this is how I learned it. And this is what helped me. So if it helps you, then you can definitely follow along with what I'm doing. So we have the design matrix is A, so just a reminder of that. So we have A transpose A. We have to do that math first, and then we inverse it. And then over here, we have A transpose L, which is my Z values, right? My observed Z values. So we calculate that, and then we can multiply the two of them together. And then we end up with the coefficients, a vector of the coefficients. Then if we need to calculate the trend, so we need to adjust all the Z values, right? So we go from our coefficients, we use our coefficients and our design matrix to adjust my observations. So now you can, if you can imagine that you have a, let's say we have points and we place a line through those points. Now we're going to find out what is the value at each individual point on that line or on that plane. And then we can find out the residuals. So the residuals, I'm going to use R in this case compared to E, because E gets really confusing. So we have our observed values minus the modeled values. So observed minus modeled. In other applications, you may see that it's modeled minus the observed. I know that that is also a case. Any of the questions that I ask will allow for both options, because all it is just a change of which ones are negative and which ones are positive. So don't stress if you're like, I don't know which one it is because I learned it this way, and everything that I do here, it doesn't matter because everything gets squared in the end. So the negative and positive is not a big deal for those residuals. So you can relax on that. So what does a first order trend equation look like? So first order, we have 3 coefficients. We have my Z observed value at each individual X and Y. We have my residuals, and we have the coefficients. So Z equals my design matrix, which has the 1s, the X's, and the Y's. There is no order because they're both first order X and Y. Then when we set up our coefficient matrix right here, and then the residuals. So we're going to kind of identify these later. Residuals kind of disappear off the map for a little bit. And then we do our transpose, and then we multiply that times the coefficient matrix, and then again that equals my design matrix, the transpose times my observations. So there's the mathematics building up, and then once you have taken this, you inverse this one, and you would multiply that by the inverse of this to identify these, right? So you have all this information, you can do it there. I will do an example of this mathematically, both by hand and in Excel for you guys, so you can see how this is done in both ways. Then we have a second order polynomial, and the second order polynomial now adds on squares. So you can see that the design matrix would start out the exact same way as the first order, and then when I go to then I would have an extra, 3 columns for the second order. So the fourth column, the value would just be x squared. The fifth column would be x times y. And then the sixth column would be y squared. Third order gets to be even more complicated, right? So we have these additional squared and cubed all along. And then we can get even more fun, right? There's fourth and fifth order polynomials. You need a lot of data. So just here, for example, with my fifth order, I need a minimum of 21 data points in order to even solve for this. And in saying that, that gives me 0 redundancy. So you probably want a minimum of 30 points just to do a fifth order polynomial. And so just so that you can get some redundancy, or not redundancy, but degrees of freedom, because you need some of that degrees of freedom to be like, okay, I'm not just solving exactly for every single one, because otherwise it's gonna say mathematically it's a perfect fit if you have 21 points, and then you show it on like your actual screen, it looks nothing like what the data is. Then we can do, after you've done that, so you've created a model, and again, I will work through an entire example with in a video in the next. I'll do first and second order for sure, and then I'll kind of show a little bit of third and the third order what that design matrix looks like. But here is something called analysis of variance, which is our ANOVA. If you do any kind of modeling, you need to calculate this. This is going to allow you to justify what you've done. You're going to give this to your client and say, here is how accurate it is within a confidence interval. So it is a very, very important component of the of modeling. Because we're dealing with math, we're creating a mathematical model, we need to justify it and say, hey, this is important. So these are all, so we have total, trend, residual, sum of squares. So SST, SSR, and SSD. There is this middle ground here that you can use. I don't suggest it though. So it does show you that you can end up with like negatives, and that becomes really hard to interpret when you end up with like a negative goodness of fit. So I don't suggest using the middle values. I suggest using these. These make the most sense. They're the easiest to understand. They always come out as positive, and you won't end up with an error. So here we have our observed values minus the mean. So the bar on top of the Z means average or mean. So take the mean of that, of like all my observed Z values, and then I take each individual one and I minus the mean from it, and then I square it, and then I add them all up. Then my trend sum of squares, I take my modeled Z values, right? So that's the L hat, and I minus the mean. Remember, the mean is supposed to be the same for both of them, for both total, or for the observed values and the modeled values. And I do all those individual points, I square it. Then my residual sum of squares is I take my original observation and I minus my modeled observation. And I do that for each point, and I square each of those, and then I add them all together. Then I can calculate something called a goodness of fit. So my goodness of fit is how well does it fit together, percentage-wise. So it's a measure of the trend versus the actual observed observations. So if there's a high error in this, but this is actually a better representation, that is fed into the R-squared values. So it's only semi-helpful. People like the goodness of fit because they're like, hey, look, this is what the goodness of fit is. But it doesn't take it that one step further to really like push it into a confidence, but it's good to know. So you're going to take SSR, which is my trend, and divide it by SST, which is my total sum of squares, and I'll get a value. If you multiply it by 100, you will get a percentage. So make sure, if I ask for a percent goodness of fit, make sure you give it to me as a percentage. Then we have ANOVA, and continuing on. So now that we've got this percentage of fit, something to look at is the average of the trend is equal to the average of the measured elevations at the reference points. Why is that? Because of the fact that the trend is actually the average based on its model, right? Because it takes all those points and tries to minimize all those points, like the residuals. And so it's taking the average amongst the entire data set. So that is why the trend average needs to be the same as the observed average. So our residual sum of squares is important because we're trying to minimize that as much as possible. And then when we are looking at our goodness of fit, what do you think and why? So is the larger better or smaller the better? Now I would leave this as a thing for you guys to answer in class, but we do want a larger goodness of fit because that makes it a better that means that it's like better good of fit is, I guess, is really what it is. Smaller means that there's less fit, and we want them to fit together. So the other thing that we need to calculate is going into our F statistics. So now we're getting into degrees of freedom, which means we're looking at lookup tables. So we have SST, SSR, those are the two important ones. So now we're looking at residuals. So the first thing we look at is SST, yeah. So we take a look at my total sum of squares, and I divide that by the number of observations minus 1. And then I take my residual sum of square, and I take that and I take m, which is my number of coefficients minus 1. I divide that. And then down here, we have my SSD, which is, so again, the modeled minus the observed. And then I take my n and I minus m, right? So number of samples minus the coefficients. And I get my MSD. So down here, MSD wants to be small, right? Because we don't want big differences between those. And MSR, that's going to be what it is mean trend, right? So we want them to be very close together. And then we calculate our F statistics. So there is a lookup table. That's what this part here is. So this first one is, it's a single tail test. And so anything that is below the lookup table value means that there is no difference between the data sets. If it is above, it means that there is a difference between the data set, and by how much. And this is all based on your confidence intervals. So this is like inferential statistics is what it's called. So H0 is my null hypothesis, meaning that all my coefficients are really the same. And then it matches, right? So we have everything that matches. If it is not, then it's going to be too large. So if this is 0, we suddenly have an infinitely large value, right? So this might be really keep getting really large. So if we have this as small as possible, it increases the F statistic, correct? Think about the math on that. So the smaller this number on the bottom, the larger this value is going to be. And so if everything equals 0 on our one-tailed test, which if you think of it as like it bumps up first and then goes down, it's down here. Anything below that means that everything is 0. So we don't want it to be 0, but we want it to match. Oops, sorry. So we want the null hypothesis to be negative in this case. But we don't want this to, because if it's really small, then it means that my SSD is way too large, right? Okay. So I'll let you guys kind of think about that a little bit. But really what I want you to do is if your F statistic is less than the lookup table value, which I will give you. So this course is not about lookup tables, so I'm not going to force that on you. So I will give you the value. And so if your F statistic happens to be lower, then you know that H null is positive, which means that yes, it agrees with the null hypothesis, and there is no difference between the trend and the residuals. The alpha, or the alternative hypothesis, means that the data sets are different. Okay, so that is what you're going to be calculating with that. So with your one-tailed test on the far end, at the far end, means everything is the same. So mathematically, you're going to calculate the F statistic and just compare, is it greater than or less than this value? And if it is greater than, then we know that all of the coefficients, the alternative hypothesis is true. Okay, so that's kind of the math behind that. Okay, normalization. So this actually doesn't have anything to do with the statistics itself. This actually has to do with singularities in your design matrix. So we have our values of x, y, and z. Z is often a, maybe 50 meters, 100 meters, 1,000 meters at the most. X is often, well, let's say if we were to use 3TM, X is about 1,000, right? A couple thousand, 3,000, 4,000, something like that. Y is 5.6 million. So as you can imagine, let's say that I'm at a low point and my Z value is like 100 meters. My Y value is 5.6 million and my X value is 1,000. Now I'm going to cube it, because I'm dealing with a third order polynomial. What happens with that 5.6 million compared to the 1,000 in the X? It causes our design matrix to become unstable. So when we try to inverse it, it's going to give us an error. So that doesn't work, right? So if I'm dealing with like small numbers like I do in my examples, easy. But as soon as I start working with big numbers, I'm going to end up with an error, and I can't have that. So here is one way of doing normalization. Now I give this to you because you might see it. I don't want you to use centroid-based computation. So if I see you using centroid-based computation in your exam or any of that, then you're wrong. Okay, because this is a weird shifted coordinate. It doesn't actually get everything to 0, and you still may end up with issues. Okay, you might still end up with singularities. So here you would take your sum of your x's and divide by n, some of your y's divide by n, some of z's divide by n, and let's say you shift your coordinates. So basically what I'm doing is finding the centroid of the x, y, and z, and I'm putting my origin at that location, and then I'm going to shift all my coordinates based on that center. So they all shift over, and then we do all of the math that I just talked about with this. So but then once you fit it, then you have to shift it back to the original coordinate system, right? Because otherwise it's really deceiving. So this is one way of doing it. It does minimize the issues that you might have in your design matrix when you go to inverse it. But a better one is true normalization. So here is, do you guys remember NDVI, normalized vegetation index? This is the exact same thing. So now what I'm doing is I'm scaling it, all of my coordinates, between -1 and 1. And that allows me to maintain the stability within my design matrix. So I have my x value, y value, z value. These are the observed ones. I find the minimum of the entire range, and I find the maximum of the entire range. And then I apply this math, and I get a new normalized coordinate. So I have to do this with all of my coordinates, every single one of them. So I normalize all of them, and then I do all the math that I just talked about up to really the end of the modeling. Once you get to the end of the modeling, you need to convert it back into the original coordinate system by denormalizing it. Now, again, I'm going to do an example, a couple examples, in my global trend video. So please do go there and follow my examples. Don't go astray. Follow them exactly, and things will be good. So you should be able to follow them. I'll show them how to do them by hand and worked out. And I'm also going to show how to do them in Excel, just so you can see the formulas in there, and I'll help you along with that. And otherwise, that is global modeling. So the whole steps that you need to do, the first step you do before you do anything is normalize your coordinates. Start with that. Then you're going to apply the least squares adjustment, or least squares estimation, to find the coefficients. Then you are going to denormalize your coordinates to find out your new z value on that model. Then you're going to calculate the R squared. Then you're going to calculate the F statistic and test for that. See if it actually fits. So those are the 5 things that you are going to do in order to determine your to determine a global model. And so again, please refer to my global model example, which will be a video. And our next lecture will be on local modeling.